Hello, in the previous videos I showed you how to find the vertical, horizontal, slant asymptotes of a rational function, and now I'm going to show you how to put everything together so we know how to graph one, alright? So let's take a look at that now, and I'm going to take you through a bunch of these examples, and on each one I want you to tell me what I call the anatomy of a rational function. It's all these parts to the function we want written down. So the first one right here is going to be y equals 4 over x minus 2. So we're going to start with finding the domain of this thing. Remember, the denominator cannot be 0. What makes the denominator 0 here? Well, it's 2, right? So we're going to throw 2 out of the domain. And we're going to say it goes from negative infinity all the way up to 2. We're going to skip over 2 and then go to positive infinity there. Now, at 2, there's either a vertical asymptote or a hole. And so we need to know which one is it. In this case, there's nothing canceling out here. That means there must be a vertical asymptote there at x equals 2. And it also means since there's nothing else giving us issues in the domain, there are no holes there. So I'm going to go ahead and grab out the ruler. You use a straight edge if you're in my class, whether it be a ruler or a folded piece of paper, and I'm going to draw the vertical asymptote. There we go. The next thing is there a horizontal asymptote? Well, notice that the degree of the numerator is 0, the degree of the denominator is 1, which means that the degree of the numerator is less than the degree of the denominator. And from our last video, we learned that that means there is a horizontal asymptote at y equals 0. Let's put that in. So now we have our horizontal and a vertical one there. Because there is a horizontal asymptote, there is no slant asymptote. You can't have both. Remember, slant happens usually when the degree up top is larger than the bottom, but sometimes, even though that's the case, there is no slant. The x-intercept happens when the y value is 0. So in this case, if I put 0 in for y and solve, I get 0 equals 4, and that's never going to happen there. So in this particular function, there is no x-intercept. Y never equals 0. The y-intercept happens when x equals 0. So if I put 0 into this, I end up with 4 over 0 minus 2, which equals 4 over negative 2, and that's negative 2. So when x is equal to 0, y's value is negative 2. So I'm going to go ahead and graph that now. At 0, negative 2, there's a point. And it tells me that I've got a curvy corner over here, right? And so that's how I'm going to draw my curve. Going just like this. Now from there on, I know that I either have a curvy corner right here or right here. Usually I guess that it's going to be opposite corner, but sometimes you get them on the same side. What it will not be is one up here, because then it wouldn't be a function, would it? So what I'm going to do is I'm going to pick a point to the right of this vertical asymptote, like point the x value of 3, and I'm going to put 3 in this function and see what I get. So when x equals 3, I end up with y equals 4 over 1, because 3 minus 2 is 1, which equals 4. So at 3, we're at 4 right here. And that tells me I have a curvy corner up here in the top right. Now, a few things to note here. What am I looking for when I go to grade this? Because I know you're not going to draw it exactly perfect. In fact, if we look at the actual answer here, this is what the actual function looks like versus what I graphed. So this is the computer-generated one. This is mine-generated. They're pretty close, aren't they? But they're not exactly the same. So when I go to grade this, this is how I typically grade them. I say, did the student get the vertical asymptote right? If they did, they get a point for that. Did they get the horizontal one right? Yep, point for that. Did they get any intercepts correct? Now, this one didn't have an x-intercept, so you don't, I can't count that off on you. But if it had an x-intercept, then I would count that as well as a point. Did you put the correct corners in the correct spots? That's a point. So in this case, this would be like a 5-point question here. Vertical asymptote, horizontal one, curvy corners in the right spot, and a correct intercept. I would also probably go through and count these as a point each. So they add up, but it allows me to give you some partial credit even if you accidentally mess up one of those spots. Now, some other things I'm looking for is you should not be crossing the vertical asymptote. You should have a function. You shouldn't have anything that looks, I mean, I know this kind of looks like a vertical line. I know, it's hard to draw by hand. But you shouldn't have any obvious things going on here that are super wrong. So as you get through these and we go through each one, we will practice them so that you can feel confident that you're getting them right. All right, let's take a look at the next one I want you to do here, which is, here, I'll write it out. X squared minus 4 divided by x minus 2. That's going to be our function. And I want you to write out that anatomy there of a rational function. You can pause the video if you want and give it a try. The first thing we want to do is figure out what is the domain. Well, once again, the domain is going to be the same here, isn't it? You've got x minus 2 in the bottom. So I know I've got to throw out 2. So you go from negative infinity to 2, and then 2 to infinity. So that means there's either a vertical asymptote here or there is a hole. I can factor the top on this one. So the top, notice, is a difference of squares. That factors to x minus 2 times x plus 2. And this is all over x minus 2. Now, does anything cancel here? Well, yeah, if you said yes, you are correct. We got x minus 2 over x minus 2. Those two cancel out, which means that is where the hole is. Or in other words, what we call a removable discontinuity. Fun stuff, right? So that occurs at 2. Now, there are no other domain issues, so I know there's not going to be a vertical asymptote. But I need to know the y location of this hole. So don't forget that. So to find the y location, don't put it back in here because you'll get 0 over 0. 2 squared is 4, 4 minus 4 is 0, and 2 minus 2 is 0. You get 0 over 0, which you can't do. So to figure out the y location of the hole, put it back into this canceled out version. This thing simplifies to x plus 2. So if you put that 2 in, you get 4. So whatever you find for the x value that the hole is at, put it into the canceled out version here. Now, the horizontal asymptote, let's see, the degree up top is larger than the degree in the bottom. So there's not going to be a horizontal asymptote. This thing simplified to x plus 2, all right? Which means since it canceled out and simplified to this right here, we're not going to have a slant asymptote. In fact, if we graph x plus 2, let's go ahead and do that so we get credit for graphing the function. It's going to look like this. We've got the hole at 2, 4. I'm going to go ahead and put that in. If I got a pencil, if I'm drawing this in pencil, you can draw the graph and then erase it. But I don't have a pencil. I've got markers here. So 2, 4. I'll go ahead and just draw a little circle right there. And then this is got a slope of 1 and a y-intercept of 2. So let's put that in. Make sure you put arrows on the end to show that it goes on forever like that. And look how nice that looks. All right. The x-intercept, we could just look right here and figure it out. Or we could say if y equals 0, where do we cross the x-axis? So if y is 0, you can take the simplified version here. Subtract 2 from both sides, you get negative 2 is equal to x. So at 0, negative 2, we can also see it on the graph, but it's nice to have that double check there. Also, if you put 0 in for x, you get positive 2 for the y-intercept. So, wait a minute, I got that backwards, didn't I? The x-intercept is at negative 2, 0. And then the y-intercept is at 0, negative 2. That's what's nice about positive 2. One of those days, right? Double check, and it's nice to have that graph there because you can say, wait a minute, I did something wrong. So that's why I make you do the graph, and that's why I make you list out all this stuff. It's not just to be like, hey, this is fun, let's do it. It is fun, but it also serves as nice double checks because even teachers mess up, right? Believe it or not. All right, so that is a case where the rational function simplifies to something that's linear, and it has a hole in it, okay? So no asymptotes, just a hole, and sometimes we will see that. Let's take a look at the actual graph. This should look spot on to the computer-generated graph of it, and it does, okay? Let's look at another one here. So this time, let's do x minus 1 over x squared minus 1. So x minus 1 over x squared minus 1. That's going to be your f of x there. You can pause the video and give that one a try. All right, I take it that you've paused it, given it your best shot. Let's see what we got going on now. So for this one, the domain, I want you to be careful with it. Yes, we can't have that denominator equaling 0. So let's do a little bit of work to figure out what makes the denominator 0. Some students will just say, I can see it right off the bat, it's 1. Because 1 squared minus 1 is 0, so we've got to throw 1 out. But be careful with these because you'd only be half right. When does x squared minus 1 equal 0? Well, that's when x squared equals 1. And if we square root both sides, we get a positive and negative 1 there because both of those will give me 1 when I square it. Or, I'm sorry, yeah, when I square them, I get 1. Another way you can look at it is this. I'm going to switch markers because that one looks kind of hard to see. If I have x squared minus 1, I could also, set it equal to 0. I could say that's a difference of squares, so I get x minus 1 times x plus 1. And then set each factor equal to 0, so you end up with x equals 1 and x equals negative 1 as the things that x cannot equal. So this thing has two things that gives me a domain error. So the domain goes from negative infinity to negative 1, and then negative 1 to 1, and then 1 to infinity. I'm throwing out two numbers, these two right here, 1 and negative 1. Both could be vertical asymptotes, both could be holes, or one could be a vertical asymptote and one can be a hole. I've got to figure that out for myself. So I'm going to go back up here at the original function, see if anything cancels out when I do factor it. And we just factored the denominator. Let's do that again. I get x minus 1 times x plus 1. And maybe you're looking at this already and going, hey, I see something that will cancel. Because it does. Those two right there. So that minus 1 right there, that's going to cancel out, which means x equaling 1, that's where the hole is. Because that's what makes this guy right here 0. That x equaling 1 there. So when x equals 1, we have a hole there. Oops, not x. When x equals 1. And up here, the other one did not cancel, so we have a vertical asymptote at negative 1. Now, I want to go ahead and figure out the y value of the hole, so when I graph this in marker, I can go ahead and put a little circle there. So I'm going to go to the canceled out version. These canceled out, you're left with the 1 in the numerator and an x plus 1 in the denominator. And I'm going to put 1 in for that x there. And 1 over 1 plus 1 would give me 1/2 there. So at 1 comma 1/2, that is where the hole is. At x equals negative 1, that is where the vertical asymptote is. So those, I'm going to go ahead and graph, let's see here, that vertical asymptote first. And then I'm going to graph the hole there. Let's pick, I'm going to do gray this time. So at 1, 1/2, that's where the hole is. Let's keep on. Is there a horizontal asymptote? Well, notice that the degree of the numerator is less than the degree of the denominator. This is like saying x to the first, this is x squared. So yeah, there's a horizontal asymptote. It's going to be at, oh, I'm switching colors. Is that going to bother someone? I bet you it is. Oh, well, I don't know what I did with the other marker. It's going to be at y equals 0. All right, so let's put a horizontal asymptote there. I know some people it bothers. It doesn't really bother me, but it does kind of mess up things, doesn't it? It's like it's highlighting that. So there's y equals 0. Because it has a horizontal asymptote, there's no slant asymptote, so none. And then we need to figure out x and y intercepts. So x-intercept happens when y's value is 0. So what makes the numerator here 0 will make y's value 0, and that is a 1. So when x equals 1, the y value is 0 there. So it crosses at 1, 0, which will be, let's see, right here. Oh, wait a minute. Can we do that? Can we cross a horizontal asymptote? Well, the answer to that question is yes, you can cross a horizontal asymptote. However, what did our domain say? Our domain says you can't put 1 in. So be careful with this, okay? Because if you put 1 in right here, you're going to get 0 in the denominator. And so, in fact, we can't do that because it's not part of the domain. There is none. Look at that, switch colors again. All right, so no x-intercept there because even though we solved and said, hey, 1 makes the top 0, so it goes to 0, remember, we threw that out of the domain, so we have an error there. We can't do that. The y-intercept happens when x's value is 0. So if I put 0 in for x, I end up with -1 over -1, which equals +1. So at 0, 1, you do have a y-intercept. And so I can start to see this curve come through like this. And if you got a pencil, I didn't do this in pencil, you can erase where we try to put an x-intercept in there where none exists. So do this in pencil. I don't do this in pencil because it doesn't show up on the camera that well. All right, let's take a look and say, I'm betting there's going to be a curvy corner down here, but just to check, let's put -2 into the function and see what we get. So if I put -2 into that function, I get -2 minus 1 over -2 squared minus 1. This gives me -3 over 4 minus 1, and that gives me -1. So at -2, I'm at -1. It's right there. So I'm going to draw my curvy corner in like this right here. Try not to go backwards like that. Try to make it look closer like it's getting away, because otherwise it's not a function. All right, so on this one, let's check out and see how I did compared to the computer-generated graph. There's our computer-generated graph. There's the actual graph. That's pretty close, you know? That's what I'm looking for. And by, once again, for the point value, because that's what everybody cares about, how would I grade this? Well, I'm making sure that you put a hole there and not a vertical asymptote. I'm making sure you put a vertical asymptote there, a horizontal one right here. Did you put this curvy corner down in here somewhere, fairly close? And did you have a curvy corner right here? And did you get your y-intercept? And yes, if you put an x-intercept there, you could be counted off a point, even though it's not on here. But so you got 1, 2, 3, 4, 5, 6, about 6 points in there. And of course, points for filling this out correctly. Remember, we don't want an x-intercept. It should say none there. So all in all, these have so many points to them. There's lots of opportunity for partial credit, which makes it nice because every once in a while, we all mess up a little bit. All right, let's try out another one. So this one right here, I've got it on my sheet. It's number 5. It says x squared minus 9 over x squared minus 4. And so I think sometimes it's just helpful. You don't have to on this. My initial urge here is to go ahead and factor the top and the bottom. So I want to say x minus 3 times x plus 3, x minus 2 times x plus 2. And this kind of helps out sometimes if you see that, hey, I can factor it pretty easily when I'm looking for these things going on. I notice nothing cancels out, so that's going to say, hey, there are no holes on this thing. Not that we need to start with that, but none there for the holes. The domain, though, I know that it can't be 2 and it can't be -2. So I'm going to throw those out. So I'm going to go from -infinity to -2. Remember, the smaller number comes first there. And then I'm going to go from -2 to 2, and then 2 to infinity. That is my domain. And because none of those canceled out, those issues with x cannot equal 2 and x cannot equal -2, nothing canceled out, that means I'm going to have two vertical asymptotes here. So one at -2 and one at +2. Let's pause and go ahead and graph those while we're thinking about them. Sometimes when I'm grading these things, students put this down and then they don't graph it correctly. So let's go ahead and graph it while we're thinking about it. There you go. All right, so that's put in. Now let's look at the horizontal asymptotes. So this thing shows that the degree of the numerator equals the degree of the denominator, which means we're going to take the ratio of the coefficients. In this case, it's 1/1. So there's a horizontal asymptote at y = 1. So I need to put that in. All right, there's no slant asymptote because we've already got a horizontal one there. The x-intercept. X-intercept happens when y is equal to 0. So what makes y equal to 0? Well, that would be if 3 went in right here for x, the whole thing would go to 0. Or if -3 went in for x, the whole thing would go to 0. So I've got two intercepts there. Let's go ahead and graph those. I've got one at 3 and then one at -3. So let's see here. X-intercepts at 3, 0 and -3, 0. The y-intercept happens when x equals 0. So looking at this up here, I'm going to put those in. So when you put 0 in, you get -3 times 3. And on the bottom, we end up with -2 times 2. This gives me -9 over -4, which equals 9/4. So when x equals 0, y equals 9/4, which is about, what, 2 1/4. So 0, 2 1/4 right there. Now's the fun part of graphing this. So right now, notice that I'm going to have a curvy corner through here. I can go ahead and graph that. How do I know? Because I got that point right there. And then I'm going to have a curvy corner over here. And now I'm going to come up here and I need to put in some test points here to the right of this and to the left. So typically when we've got these two with vertical asymptotes, all right, there's a couple of things that happen. Let's look at some patterns that I can show you. So let's say we've got two vertical asymptotes and a horizontal. I'll do a couple here for you to follow along with. Usually the way the pattern looks is this. You can have what we've got currently, where they're on the same side of that horizontal. You can also have them up here on the same side, right? And if that's the case, this one in the middle kind of looks almost like a parabola in the middle. Same thing down here, but it's never like on the same side. It's going to go like opposite down here below. And then you can have the case, let's draw two more actually. You can have the case when they're in opposite corners like this. And in this case, it's going to look kind of cubic coming through here. So it's almost like, imagine this like being like a knee and it gets bent over. It's going to curve like this. The same type of bend in that curve. Same thing right here. It's going to curve in that same manner. It's going to curve like this, and they connect right here to kind of look a little bit cubic. It's not quite the squiggle I was wanting there. So let's draw it again up here, but with this corner and this corner right here. So notice if you just kind of shift this over and shift this one over into the middle, it would have a curve kind of like this. Notice how that kind of like dents that line this way and this one dents that line that way. Those are your basic patterns you're going to come up with in here. So this one follows this first one we looked at. It should almost look kind of like parabolic going through here. Now, if that doesn't convince you, what can you do? Well, you can try some test points out. If I put 1 into the function, where am I? So if you put 1 in, you end up with, negative 8 over negative 3, which is 8/3. So you go over 1 up 8/3. That's almost at 3. 1, 2, 3. Almost right there at 3. Same thing if you put in negative 1, you're going to get the same value, right? So negative 1 goes in, you're going to get negative 1 squared, which is 1. Same thing is going to happen, and you're going to be right there like this. And so now we can say for sure, like, hey, this thing is going to look almost like a parabola squeezed in between these two vertical lines there. And that is the shape of our graph. Let's check it out compared to the computer-generated one. Look at those right there. Pretty darn close. All right. So with that being said, let's take a look at another one. Oh, by the way, let's go through the grading on this. So for the grading here, I'm making sure that you gave me 1 for that vertical, a point for that vertical, a point for the horizontal, a point for the x-intercepts, a point for the curvy corner being in the right spot, a point for the y-intercept, and a point for this shape in here being correct. Okay. And of course, you don't lose, you lose points. Sometimes students add more to a graph that needs to be there, like maybe another part to it, and you'd lose points for that. All right, let's look at the next one. All right, I want you to try out number 6. And if we look at this, like I said before, it helps if we just kind of factor some things out. If I've got in the numerator, notice there's a 2 in common, and I get x cubed minus 1 over x cubed minus 1. So I will have some things here that do factor, but before I do that, let's make sure we take note of the domain. So can't talk. The domain, I'm going to throw out 1 because it makes the denominator 0. Notice 1 cubed gives me 1, and 1 minus 1 is 0. Negative 1 doesn't do that to me because negative 1 cubed is negative 1, and negative 1 minus 1 is negative 2. So we need to go from negative infinity all the way up to 1, skip over 1, and then go to infinity. Because these cancel, it tells me that this issue where x cannot equal 1 is not a vertical asymptote. So I have none there. I do have a hole, though, at 1 comma something. So what is that something? Because these two right here canceled, I'm left with just 2. So this hole should be at 1 comma 2. There's nowhere I can plug in the x. It's just at 2. And you'll see, when you see the graph, you understand why that's the case. There is no horizontal asymptote because the degree of the numerator equals the degree of the denominator. So none here. And there is no slant because if you divide this thing out, you end up getting just 2. There is no slant asymptote there. If we graph this, this is what it's simplified to. We need to make sure that we place the hole in there at the correct spot. So when I go to graph it, that removable discontinuity is at 1 comma 2. And I'm going to go ahead and put that circle there because I'm graphing in marker and I don't want to, I can't erase it. So I don't want to have a spot there. Now this is y equals 2 is my graph. It's a horizontal line at y equals 2. Just like that. So what's the x-intercept? There is none, right? In fact, you could test that out. X-intercept happens when y equals 0. So you say, okay, when does 2x or 2x cubed minus 2 equals 0? Well, that's when x equals 1. But just like we discovered on the other one, if I put 1 in here, that's fine. But what's not fine is that the domain we threw out x equaling 1 because it makes the bottom 0. So even though this simplifies to a horizontal line at 2, you can include 1 in the domain, which means you can't ever let x equal 1. There's no x-intercept because you can't let x equal 1. The y-intercept happens right here at 2. So when x is 0, y equals 2. And there's our graph, okay? Usually, we're talking about points for this. Usually when I run into issues with this, grading it, it's because a student did more than what they needed to do. They're putting in vertical asymptotes, they're putting in curvy corners, all sorts of things here that will mess you up and lose points. And so most of the points are just coming through here and making sure you did those, the y-intercept, the line's graphed correctly and there's a hole in it, you know, you get points for that. Let's look at the next one. So this next one here, notice we've got two quadratics, one in the numerator, one in the denominator. And like I've said before, it's going to be helpful if we just go ahead and factor both of those. So pause the video and factor it. And I take it if you've paused it and you factored it, you should have gotten something like this. X minus 4 times x minus 1 in the numerator. And in the denominator, you should have gotten x plus 2 times x minus 1. Now this helps us with a couple of things. First, with the domain, I know that from this factor, x cannot equal negative 2. And from this one, x cannot equal positive 1. So the domain is going to look like this: negative infinity to negative 2, and then union with that negative 2 to 1, and then 1 to infinity. So I've got two issues with the domain. Once again, we're either going to have two vertical asymptotes, or we're going to have two removable discontinuities, or two holes, or I'm going to have one vertical asymptote and one hole. So let's see, does anything up here cancel? And the answer is yes. We've got some things canceling out. We've got x minus 1 cancels x minus 1. That means that that issue right there is a hole. X equals, or x cannot equal 1. This is my canceled out, or my reduced form of it. If I put 1 into it, I get 1 minus 4, which is negative 3. And in the denominator, 1 plus 2, which is positive 3. And that simplifies to negative 1. So when x equals 1, y equals negative 1, that's where the hole is. And that's, I'm going to go ahead and graph it now so I don't forget to graph it. So 1, negative 1, put that space right there missing. Now the vertical asymptote occurs at negative 2 because that did not cancel. So x equals negative 2, make sure you put that as an equation, x equaling something. And I'm going to go ahead and graph that vertical asymptote while I'm thinking about it. All right, so there it is, graphed for us. Now the horizontal asymptote, because these degrees are the same, you take the ratio of the coefficients, which is going to be 1. So it's going to be y equals 1. Look at that, I always switch colors there for some reason. Let's go ahead and graph that. There we go. That also means I have no slants there, because you can't have a horizontal and a slant at the same time. And I want to know what the x-intercept is. So when does it cross the x-axis? It's when y's value is 0. So if I set the top equal to 0, a few things here. This one canceled out. I don't want to include 1 there because remember it's not part of our domain. But x minus 4 I can still set equal to 0 and solve that. So when x equals 4, y's value is 0. Let's go ahead and graph that point, 4, 0. And you kind of imagine this curvy corner coming through here, and I bet you we're going to have a y-intercept right over in there. I also know that because I've already seen the answer, right? Anyway, the y-intercept happens when x equals 0. So if you put 0 in here to this canceled out form, I end up with negative 4 over 2. And negative 4 over 2 is negative 2. So at 0, negative 2, I've got a crossing right there on the y-axis. So I can already tell that I can draw my curvy corner like this coming through. And now, once again, I'm going to bet that it's right here, but it could be over here. Let's do a test point. So if we go 1, 2, 3, we'll do negative 3. Put negative 3, and you can put it into the canceled out version. Negative 3 minus 4 divided by negative 3 plus 2 equals negative 7 over negative 1, which equals positive 7. So at negative 3, I'm at 1, 2, 3, 4, 5, 6, 7 right there. And that's how my curvy corner is going to go through like that. All right. I'm not going to go through the point system on this, how I'd grade it, because I feel like you're figuring that out now. But if you have a question, let me know. There is the actual computer-generated graph of it. And it looks just as beautiful as my graph, doesn't it? All right, except for it's lacking color. Let's look at the next one here. All right, this is the next problem I want you to try out. And remember, what are we going to do before we do anything? Trying to graph this and figuring out all this mess, we want to factor it. So pause the video and factor it. And I take that, you've done that now. So let's factor the numerator. You should have gotten x minus 1 up top and times x minus 6. And then in the bottom, 2 times x minus 1. So what makes the denominator 0? 1. If you put a 1 in, it's going to go to 0. So we need to throw it out of the domain. Negative infinity to 1. And then 1 to infinity. So there's either a vertical asymptote because x cannot equal 1. It's either a vertical asymptote or there is a removable discontinuity there, right? And does anything cancel? That's our next question. Looks like x minus 1 and x minus 1 do cancel. So that tells me that this must be a hole right here. And because that's the only domain issue, that means there are no vertical asymptotes. So if I put 1 into the canceled version, I end up with negative 5 over 2. So at 1 comma negative 5 over 2 is where the hole is. Let's go ahead and graph that so you do not forget it. Remember, all this stuff we want to eliminate silly mistakes. So go over 1 and then down 2.5 and put a hole right there. Now, horizontal asymptote. I notice that the degree of the numerator is greater than the degree of the denominator, which tells me there's no horizontal asymptote. None. Now this thing canceled out to x minus 6 over 2. So the next question is, do we have, well, actually, let's just go ahead and simplify this. So if you look at it like this, that's the same thing as saying x over 2 minus 6 over 2. And x over 2 is another way of saying 1/2 x minus 6. So this is the equation right now. It's a linear equation. That's an equal sign right here. It is a linear equation, and so there's no slant asymptote. Because it canceled out to something linear. Let's go ahead and graph that linear equation. So it's in that format, y equals mx plus b. I can quickly see that my y-intercept is going to be at 0 comma negative 6, right? You've done this since Algebra 1. 1, 2, 3, 4, 5, 6. Put a dot. The x-intercept is when y equals 0. So let's solve that. Add 6 to both sides. Multiply both sides by 2, you get 12 is equal to x. So when x equals 12, y equals 0. There's your x-intercept. It's going to be no, something's not computing here, huh? Add 6. Oh, it's negative 6/2. See, this is why we do all these checks, because I make mistakes. You know, this is a long video, so I get worn out as I go through it. Hopefully it doesn't take you as long to go through these problems because you're not explaining it to anyone. But I understand you're learning it, so it might take a little bit longer. I should have made that negative 3, which changes a lot of things, doesn't it? That makes this intercept not 0, negative 6, but 0, negative 3. And it doesn't make, that's not going to be the case. Here, let's just start over here. We get y equals 1/2 x minus 3. Add 3 to both sides. This is 0 now. And you get multiply both sides by 2, you get 6 is equal to x. So when y is 0, x is 6. So you've got 1, 2, 3, 4, 5, 6 right here. And then you've got 0, negative 3. Now those look like they line up. There's no fake math here. I include my mistakes, because you need to know the teacher is human also. And most of you that have me as a teacher are very well aware that I'm human. All right, so that's our equation, that's our graph right there. Let's take a look at the computer-generated graph and look at that. Matches up pretty nicely there. All right, this one right here, we know we're going to have to factor it because that's what we've been doing, right? So let's go ahead and factor this one out. X minus 1 does not factor, but in the denominator we can factor this to x minus 2 times x plus 2. Notice right off the bat nothing cancels, so there are not going to be any holes. But we still have issues with the denominator when x equals 2 and x equals negative 2. We got some issues there. They cannot equal that. So the domain has to throw those out. So negative infinity to negative 2, negative 2 to 2, and then 2 to infinity. That's our domain of the function. That also means that this is where our vertical asymptotes are. We have two of them, one at negative 2 and one at 2. Let's graph that. There we go. The horizontal asymptote, well, the degree of the numerator is less than the denominator, so there's going to be, look, I'm going to switch it again. It's going to be at y equals 0 because numerator's degree is less than denominator's degree. Go ahead and graph that. The slant asymptote, because we have a horizontal one, we automatically know we can't have a slant. And then we've got x-intercepts and y-intercepts. X-intercepts happen when y equals 0, and y can only equal 0 here when the numerator is 0. So when x equals 1, notice the numerator becomes 0. You could also, if it's not as easy to see, you set the numerator equal to 0 and solve. Make sure that that is not thrown out of the domain. It's not. So we can say x equals 1, y equals 0. Let's go ahead and put that point in. When x is 1, y is 0. Right there's 1, 0. And then we have another one over here. Let's see, well, not another x-intercept, but we've got a y-intercept we've got to figure out. That happens when x equals 0, where are we crossing the y-axis? So you put 0 into this mess up here, and when I do, I get this. Negative 1 in the numerator, and negative 2 times 2 in the denominator, which gives me positive 1/4. So when x equals 0, y equals positive 1/4. So 0, 1/4 like that. And that's all I really got to graph this thing. And so it goes back to that problem we had a few problems ago. Let me pull that sheet up. This one right here, remember that? Maybe you're watching this in just little segments here, so you can always rewind the tape and see this. It's going to be one of these patterns, and I'm thinking it's going to be one like this right here, because notice you can kind of see that turn coming through right here. But we need to put in a few test spots. So here's what I like to do. We've got x minus 1 over x minus 2 times x plus 2. And I'm going to put in some test points here. So if I go out really far, like a positive 3, I'm going to get 3 minus 1 over 3 minus 2 times 3 plus 2, which gives me 2 over 1 times 5, or 2/5. So we've got when x equals 3, y equals 2/5. 1, 2, 3. Did I get that? Let's see. 3 minus 2, 3 plus 2. When x equals 3, y equals 2/5 right here. And make sure that's right. That's not, oh, it is. It is right. Okay. That makes sense, because if it's bending like this, this has to bend like that. Okay. Next one. Let's put in, I'll do a different color because otherwise this is all get messy here. Let's put in 1, 2, negative 3. So if I get negative 3 minus 1, negative 3 minus 2 is negative 5. Negative 3 plus 2 is negative 1. And I end up with negative 4 over 5, so negative 4/5 here. So when x equals negative 3, I've got negative 4/5, which is right there. And so what this does is this tells me I've got a curvy corner in the top right and a curvy corner in the bottom left here. Let's put that in. One right there. One right here. And now I got to figure out what's going on with that middle. If we go back and look at that little guide I showed you earlier that we come up with, it looks like it's going to have that cubic look to it. That one we graphed on number 5 here, we had that parabolic look going to it. And notice it followed that pattern. This one is following this pattern right here. And we can see that. It's going to come through like this, cross the y-axis right here, cross the x-axis right there. And notice this bend right here, remember if I said it looks like it's pushing it in like this, and this bend right here is pushing the graph in like that. And that's how I kind of remember it. So that's what I'm looking for on this. If I was giving you points for it, I make sure that you put this curvy corner in the right spot, this one in the right spot. You should have that cubic look going on in the middle. You should have an x-intercept and a y-intercept in the correct spot. Vertical asymptote here, and a horizontal one there. So there are several points that I'm looking for on that graph. And then over here, all of these things listed out, I'm looking for each one of those as well, of course. Let's look at the actual graph. Computer-generated one right here. Notice how well they match up. That's pretty close. In fact, mine looks better because it's in color, right? All right. Let's look at another one here. So this one, I'm actually going to take it a step back and make sure that you can always graph the easy ones as well. And so sometimes I give you all those hard ones and you see an easy one, you're thinking like, is he doing something tricky here? This seems too easy to be true. It's not. This is the parent function 1 over x. And so you should be used to what it looks like. But let's see, now that we know all these things about rational functions, let's apply it to it and make sure that we know how to do that. I know that the bottom cannot be 0, so we throw 0 out of the domain. And then we've got, let's see, nothing canceled out, so there are going to be no holes. And the vertical asymptote, not v, but x, is going to equal 0 there. Let's go ahead and graph that so we don't forget to. The horizontal one, because the degree of the numerator is less than the denominator, we have a horizontal asymptote at y equals 0. And so notice, now we're going through and doing this parent function not just by memorizing and saying, I know 1 over x has this, and we're just going to plot a few things. We actually have understanding behind what we're doing here when we're plotting or graphing the parent function. There is no slant asymptote. The x-intercept happens when y equals 0. Well, if you let 0 equal y here, there's nothing I can put in for x there that will make that a true statement. So there's not going to be an x-intercept, which makes sense. We know the graph. The y-intercept happens when you put 0 in for x, and that's a domain error, isn't it? So there's not going to be a y-intercept. And then we can actually just put in a test point to figure out where our graph is going through. So you put 1 in when x equals 1, y is equal to 1. And so it goes right there. I know I've got a curvy corner coming through right here. And when x equals -1, we're going to do a test point to see which quadrant the curvy corner is in over here. Well, 1 over -1 equals -1 also. So -1 right there. And then I want you to draw your curvy corners. Now for the parent function 1 over x, I do expect these 2 points to be graphed, okay? And then we're going to draw our curvy corner going through like this. And once again, we can compare it to the computer-generated one, and it looks pretty good. All right, let's try the next one. So this one right here almost looks like the last one, except for now the x in the denominator is being squared. So we can still factor it if you want to, but it doesn't really matter. You get x times x in the denominator. You still got to throw out 0 from the domain. So we're going to go from -infinity to 0, skip over 0, and then go to +infinity. That means since nothing canceled, there are no holes again. And the vertical asymptote is at x equals 0. Let's go ahead and graph that one. There you go. And then the horizontal asymptote, once again, because the degree of the numerator is less than the denominator, you have a horizontal asymptote at y equals 0. Let's graph that again. So you're starting to think, this is going to look exactly the same. But it's not. There's y equals 0. There is no slant asymptote. None. Now, to find the x-intercept right here, you need to know, all right, when y equals 0, what makes this go to 0? What x value makes this 0? And just like in the last one, there's nothing I can put in here that's going to make that 0, so this is going to be none as well. And for the y-intercept, when you put 0 in for x, then you get an error, right? Because it's not part of the domain. So there's none right there as well. And so that leaves us with almost look at this. Let's pull back the last one there. Look at these anatomies here. They're exactly the same, aren't they? But the graphs are going to be different, and it all goes back to these test points here. So I'm going to put 1 into the function. When x equals 1, I get 1 over 1 squared, and the output is 1. So even that point is the same, and I'm going to have a curvy corner coming through like this. And notice so far it's matching up with this graph right here from the last problem. But now I'm going to put negative 1 in and test that. Notice 1 over negative 1 squared gives me 1 also. And so now my curvy corner is looking like this. So it kind of has like a fountain look to it. And notice the difference in the graphs between 1 over x and 1 over x squared. So there is a difference there, although they share a lot of those same properties. And if we compare this to the computer-generated graph, that's what we get right there. So that's good stuff. All right. Let's look at one more question. So there's your function. I want you to take a moment and factor that denominator and see if anything cancels. All right, factoring that out, you should get x over x times x minus 1. And so what do we throw out of the domain? Well, the bottom equals 0 when x is 0 or when x equals 1. So these are two values of x we have to throw out of the domain. So we go from negative infinity all the way up to 0. Skip over 0, go to 1. Skip over 1, go to positive infinity there. So that's what we're throwing out. Now, these are either going to be vertical asymptotes, holes, or a combination of the two, right? Does anything cancel? Yes, it does. X and x cancel, and this thing simplifies to 1 over x minus 1. And so I know that because the x canceled, that 0 right there is going to be a hole. And it's a hole when x is, let's see here, put it back into the function. 0 minus 1 is negative 1. You get 1 over negative 1, which means 0 comma negative 1 is where the hole is. Let's graph that so we don't forget. 0, negative 1, hole right there. The vertical asymptote happens where the spot is that it doesn't cancel at x equals 1. Let's draw that so we don't forget. Vertical asymptote at x equals 1. There's a horizontal asymptote. Let's see, the degree of the numerator is less than the denominator. So we have a horizontal one here when y is equal to 0. Let's graph that so we don't forget. And let's see, here can't be a slant because we have a horizontal asymptote, so none right here. The x-intercept happens when y is equal to 0. The numerator can never equal 0, so y is never going to equal 0, and there is no x-intercept going on, so none right there. And if I put 0 in for x, I do get a value of negative 1, but the problem is it's not part of the domain. In fact, that's where the hole is when x equals 0. So there is no y-intercept there. And now I'm ready to do some test points to try to graph this thing. I can already tell that there's going to be a curvy corner down here because they put a hole in the graph right there, but you could try it out, put in -1 and see what you get. We can put it into this canceled out version. If you put when x equals -1, if we put that in, I end up with 1 over -1 minus 1, which equals 1 over -2. So at -1, I'm at -2, right? -1, sorry, not -2, -1/2. I was like, that's not going to look like a curvy corner. And there we go. And then if I pick a point over here like +2 and put it into this thing, I get 1 over 2 minus 1, which equals 1. Right? And so at 2, we're at 1 right here. Now there's a couple of ways you could have graphed this. You could have done those points, or you could have recognized that, hey, the parent function of this reduced form, or simplified form, is 1 over x, and it's paired, this right here is paired, the -1 is paired with the x, so this is a horizontal shift to the right 1, and notice that's just 1 over x, what we had a few moments ago, and it's shifted to the right 1. And then because of its past, where you had to cancel out those x's, you put a hole in the graph right there. All right. So that is it's the last problem I'm going to do in this video, because this thing is approaching 1 hour. If you've stuck with me through this whole video without stopping, congratulations, you've earned a medal. Hopefully what you did is, you've seen the problems and you were able to skip around to the one you needed help with. There is one thing we did not cover, and that is slant asymptotes and how to graph those, and sometimes we do have holes in those graphs. So I'm going to make a separate video for that. I myself need a break after an hour's worth of work here. And so if you need help with those, we'll do some more problems with graphing rational functions next time. Okay? Thanks for watching, and let me know if you have any questions.